Hi everyone, welcome to the webinar on engineering strategies for airborne diseases. My name is Fanny Wu, an architect at Gensler San Jose, a co-chair of the AIA Silicon Valley Committee on the Environment. The experts from AlfaTech will be sharing engineering recommendations to reduce the risk of transmitting airborne diseases within buildings. AlfaTech has worked on some of the most innovative and creative projects for firms such as Uber, LinkedIn, Airbnb, Kaiser, Stanford, and Genentech. We have three speakers today. Jeff Finney is the founder of AlfaTech, has over 35 years of experience in the engineering design development of projects and working on projects worldwide for numerous high-profile firms. Corey Kaya is a principal engineer with AlfaTech, based in San Francisco, a mechanical engineer with over 15 years of experience. He is committed to HVAC innovation and evolving the field to meet the needs of high-profile clients and their environments. He is a licensed mechanical engineer and a lead accredited professional. Robert Nexdorf brings 20 years of electrical engineering and project management experience. He is an expert in complex electrical system designs, managing aggressive construction schedules, and achieving high sustainability standards. We welcome our speakers today, and please use the question box to submit any questions. We will be monitoring it throughout this session. And I'll pass it to Jeff Finney.
Thank you so much, Fanny, for the introduction. And hello, everyone. Again, this is Jeff Finney. I'm the CEO of AlfaTech. Just quickly to let you know that this is probably the 20th webinar and seminar that we have been giving to the clients and different associations just to make sure everybody is updated about what's going on. Obviously, this COVID is in everybody's mind for the last 4 or 5 months. And just quickly let you know that we have started on this about 4 months ago when the COVID started and everybody was worried about the virus distribution and workplace and how we are going to go back to our workplace and what we're going to do with the environmental concern. So we have started on doing our homework and our due diligence on, especially as related to mechanical, HVAC, and electrical. And we spent a lot of time on preparing the report you're going to see today. At the same time, our clients, which is most of the Silicon Valley clients, they start asking the question of what they're going to do when they go back. And in conjunction with the other engineering firm in the Valley, this report we established that one thing I was going to mention it to you guys that this is not we don't really have the data prove all of this. This is mainly a recommendation, and we have been recommending it to our clients. We are actually implementing it for some of the clients like LinkedIn and Visa and other clients. But this is the hope to minimize the distribution of the disease as people go back to work. Today we are going to have two and the three of us going to be presenting it. Obviously, Cray and Robert are going to talk about the technical part of it. This is just a quickly to show who we are to you as AlfaTech. Some of you already know us, but I started the company in Silicon Valley. We are all over the world right now, and our services is very much concentrated on mechanical, electrical, plumbing, fire protection, and also on the technology side, plus the lighting design and commissioning. And as far as the location, we are in California, located in San Jose, San Francisco, and Los Angeles. Then we are also located, we have locations, 65 other locations in the world. And the total company is about 6,500, but our primary concentration is really on engineering side more than anything. And then as far as the core market that we have been involved, campuses, corporate campuses is our focus point, and that's our primary concentration on campuses. And this report that we are giving it to you is really more related to office space environmental that is going to have people in it. We also work on the corporate TI, mission critical, higher educational, life science, healthcare, and residential and public areas. So our really core business has been all pretty much covering a lot of different sectors. And then the people that you're going to hear from today, myself, Jeff Finney, as Fanny mentioned, I'm the founder and CEO of AlfaTech. I'm also mechanical electrical engineer myself. Then we have Corey on the mechanical side that he's going to give his report, who actually he's the one who initiated originally, and Robert on the electrical side. So Corey, just to jump into our report, and I pass it to you then.
Sure. Thanks, Jeff, and good afternoon, everyone. As building professionals, we have a responsibility to provide a healthy work environment to the building occupants. Today, we will be covering some engineering recommendations to reduce the risk of transmitting airborne diseases within the buildings. However, I'd like to emphasize that all these recommendations and the technologies we are going to be going over are secondary to current public health recommendations. Additionally, the primary way of transmission of the current coronavirus is close contact from person to person. Its airborne viral transmission beyond 6-foot space was not confirmed by authorities, including CDC or WHO. So ideally, we just want to see what we can do with our systems and how we can help to reduce the risk. And again, this is very important. This is only after all the other precautions taken in place, personal distancing, PPE, masks, and all the other stuff. In terms of the actual diseases, I'm sure everybody's hearing about droplets, the sizes, nuclei, or microns and all that. So just to give you a quick understanding, the typical viruses change from 0.02 microns to 0.4 microns. And just to put things in perspective, human hair is about 50 microns, 50. So we are talking about very, very small diameters over here. Coronavirus is 0.16 microns, its aerodynamic diameter. But on the other side, the viruses do not move that by themselves. So they transfer in the space through droplets, and these droplets change from 0.5 up to 100 microns. So there are the large droplets, and which are the main reasons for distancing at the moment. So as you can see, these move up to 2 meters, about 6 feet, and they are pretty heavy. They just drop. They do not stay up in the air for so long. The smaller droplets on the other side are called droplet nuclei, are usually smaller than 5 microns, and these can actually stay up in the air for quite some time. So like, for example, 10 micron droplets can stay up in the air for about 7 minutes. 2.5 micron diameters can stay about 100 minutes. And again, we talked about the main transmission. It is usually that within 6 feet person-to-person contact. But on the other side, there are some cases where nobody could track the transmission to anything else, and it looks like HVAC systems or exhaust systems could be the main reason for transmitting the diseases. We will provide this presentation later on, and then you will see some links over here. If you have time, you can check those. So the Wells and Riley equation has been utilized in hospitals mainly to capture or calculate how the disease is spread. So they pretty much look at, I mean, there's a lot of numbers, and it looks like a pretty crazy formula over here, so do not worry about it. Pretty much the main takeaway over here is with our HVAC system, the only thing we can control over here is Q, which is the flow rate of uncontaminated air, or it is the ventilation air we are pumping into the space. So if we can increase this, then it reduces the number of new infections. In terms of ventilation, the outside air has high bacterial diversity, but very low average of pathogens. Indoor air is on the other side, is very clean, so it doesn't have very much VOCs and all that, but the pathogen contamination can be higher. So increasing the building ventilation rates is going to help us dilute the building. So when we say ventilation rates, we are not just talking about the total supply air into the space. We are talking about how much outside air is in that supply air. So at the moment, there is not really any clear metric for how many CFM per person or what the air changes, but the more the better. Back in the day, during the original SARS outbreak in China in 2003, they actually utilized CO2 sensors and determined about 500 to 550 parts per million is a good indicator. And just to give you an idea, outside air in the Bay Area is about 400, slightly less than 400 parts per million for CO2 concentration. With forced air systems, we actually have air side economizers, and which is pretty much the majority of the buildings, especially over here in Bay Area. Because of our climate, we can utilize air side economizers throughout the year. With these systems, we can actually increase outside air with no problem. There's going to be some capacity issues and all that, but at least we have the means. But if you have a building where you are utilizing radiant systems or fan coils or chill beams, then this is not going to be as simple as that. And on the other side, when we are bringing more outside air into the space, we need to pay attention to where our building is located. It can be right next to a freeway or any other pollutant sources. So if that is the case, we also take other precautions to make sure that we are providing clean filtered air into the space. Air filtration, this is what we have been using in our HVAC systems to capture contaminants. So the typical system, it is called mechanical filtration or passive filtration. We are pretty much moving air through our filter, and we are capturing particles. And depending on how many of those particles we can capture, then we provide efficiency value for that filter. They utilize 12 different particle sizes for these filters, from very small, very ultra-fine particle sizes up to coarse particle sizes. And they look at the efficiency for every single one of those. And whatever the worst case is, then it becomes our MERV rating, MERV efficiency. It looks like 0.3 micron is the most penetrating size. Larger particles are somewhat easier to capture, and the smaller particles, surprisingly, are actually easier to capture. But 0.3 micron is that area where it is small enough to go through fibers in the filter, and it is also large enough not to move as much. Because with these smaller particles, they just keep moving around and bouncing and bumping into each other, bumping into fibers, so it is much easier to capture those. In terms of the MERV ratings, MERV 13 is the minimum rating to capture airborne viruses in buildings. MERV 14 or 15 are preferred. So the main difference between MERV 13 and 14 is actually for the ultra-fine particles that are smaller than 0.3 microns. With the ultra-fine particles, MERV 14 filters are going to be about 10 to 15% more efficient than MERV 13 filters. Then there are the HEPA filters, which are mainly used in clean rooms or lab environments or hospitals. These are actually much more efficient. They can go up to 99.97%, which means only 0.03% of the particles stay in the airstream. They are very efficient, but the pressure drop to move air across these filters is pretty high, and it is not really going to be feasible to install these on a typical office or commercial building filtration systems. We can take a look at it case by case, but in most of the times, this is not going to be feasible. And on the other side, there are carbon filters. We have been utilizing these filters mainly for odor control. They are actually good, very good with VOC control as well. But in terms of airborne diseases, they are not going to provide any benefits. And in terms of the filtration methods, as we talk about. Straining is one of them, and it is just like a fishnet. So you just capture whatever is larger than the actual opening sizes on the filter media. But then there are other methods, inertial impingement, interception, Brownian diffusion. So these are all making it possible to capture smaller particles that are much smaller than the actual openings in the filter media. And then there is dynamic filtration. The main difference between dynamic filtration and the mechanical or passive filtration is we polarize the particles, the fibers, and the screens within the media, and with the electrostatic effect, then we capture particles. Because of the electrical field, we can capture particles all around the media, not only at the face of the filter, which then gives us a much longer filter life. A typical MERV 13 filter, for example, you would replace every 3 months. With the dynamic filtration, you can replace those within years. So actually, these were utilized in Astra headquarters in Georgia, and they utilize the same filters up to 5 years without any maintenance. The main drawback on dynamic filtration is the price. It's much more expensive than typical filtration, but on the other side, the pressure drop is much less than a typical filtration. So depending on the application, they can become very helpful. When you look at life cycle analysis for a typical commercial office building, they usually do not make the cut. But when you look at capturing airborne viruses, when you look at capturing VOCs, they can be pretty effective. And on the other side, because of the longer filter life, you will have less filter change out, which is also reducing the carbon footprint of the building. And then we have the local filtration options. When we have high contamination, high traffic areas, or like restrooms, break rooms, these can be pretty handy. We can either locate those on the floor, on wheels, on coasters, or we can have them up in the ceiling. We can have HEPA filters in these. We can have UVGI technology, PCO technology that we are going to cover later on during this presentation. We can also include humidification. And then there is bipolar, needle point bipolar ionization. This is a different capture technology. With this, we are generating ions, and these ions are either positively or negatively charged, and then they attach to the small particles. And then because with the different polarization, they will then create a magnetic effect, and different positive ions will attach to negative ions or particles in this case, and they will become much larger. So this actually targets that 0.3 micron, the most penetrating particle size, and make those much larger. And they become large enough to be captured in the filtration system, or they become too large that they drop on the floor, and then during the regular clean out, they are just removed from the building. With the viruses, they just combine on the surface of the pathogen, and they remove hydrogen because of the additional electron they need from the space, from the virus. So when the virus loses a hydrogen, then it cannot replicate itself and becomes inactivated. This system has been in place for quite some time, for over 100 years, and the older technology called corona discharge. The older technology actually utilized a different way to create a electrical circuit, and with that system, we could not control how much power we are generating. The main drawback on that system is it also broke oxygen molecules in the space and generated ozone. With the bipolar technology, then we are not worried about ozone generation. The system is very flexible and fairly cost effective. It can be installed within air handling units, within ducts, within fan coil units, even in split system ductless fan coil units or ceiling cassette units, and they are also self-cleaning. And then there's the UVGI technology, and Rob is going to provide us with more information on this.
Hi. So ultraviolet light is a technology that's been in use for quite some time for mitigating germs, bacterial organisms, primarily used in the food industry to this point. But again, this is something that can be effective at killing or deactivating viruses. Viruses are not actually living organisms, so the UV light just simply deactivates them. So by doing this, it's UVC. You're all familiar with UVA and B, which are common radiation from the sun, causes sunburns. UVC is the shortwave ultraviolet light that's typically between 100 to 280 nanometers. And so this has actually been found somewhere in the 265 to 270 nanometer range. It's been proven to be effective for deactivating viruses. So there's a couple of ways it can be implemented into a space. One is putting it within the air handling system, typically within the return air, so it can disinfect the air that's being returned through the system. Another option is to place it in the room. It's got to be above the occupied area, which I'll get into in a minute here. Or also it can be used throughout the space in non-occupied areas, typically used by robots moving throughout the space. This is a low energy solution. You know, the wattage is pretty low, typically for like an air handling system, you know, for say 100,000 square foot building, you're looking at 2 to 3 kW total. It also doesn't count against any energy budget, so it's Title 24 friendly because it's more considered a process as opposed to actual light that's used. If it's in the air system, usually, you know, the ideal conditions are around 200 to 400 feet per minute and around 80 to 95 degrees. Like I said, for the return air, is usually where it's most effective. Next slide. So, as we talked about, for within the space, usually use the upper range of the upper area of 7 feet. And this is, again, while UVC does not cause sunburn, it can cause some irritation to the, particularly to the eyes for exposure. When it is used within the space, sometimes this can be more effective because, you know, you think about, you know, the contaminants for infection, everything are moving sort of person to person. So, you know, if somebody coughs or sneezes and expels germs into the air, they may have to travel a long way till they get to the air system again. So having UV within the space, sometimes if it works well for the application, it can be very effective. Usually need some sort of a, you know, circulating fan to help move air, more consistency throughout that space and get it into the disinfection zone. You know, again, it's not something you want to have people exposed to for long periods of time. You know, maintenance staff would need to be trained properly so they're familiar with the system, how to turn it off if they need to, you know, get up into the ceiling for something that they're not exposing themselves. In an unoccupied room, you know, there you have a little more flexibility because there aren't people there. You can run robots through with high-powered lamps that can disinfect the air or disinfect surfaces faster. Although for surfaces, you know, UV is not the best way for disinfection, only because the UV lights can only disinfect what they can see. So, you know, unless you're going to run it, you know, underneath desks and chairs and everything, or underneath doorknobs even, you're not going to hit every surface. So in that respect, you know, your best option is for, you know, your traditional cleaning products to disinfect surfaces. As far as installation in the air handling systems, UV can also prevents mold and fungus buildup on your cooling coils for the system. You get some additional pressure drop again on your system as well. But then also, one of your main benefits here is the UV lighting is not going to be, nobody's going to be exposed to these when they're in the air handling system. So you can use higher powered lamps to essentially disinfect the air faster.
Correct. So pretty much the UV dose in any system, it's either in spaces or in air handling units or ductwork. So the UV dose is pretty much the intensity, which is the irradiance over here, times the exposure time. So the main challenge with the air handling units is you get just that single pass, and that's the only exposure time. But on the other side, because we are not concerned with human exposure, we can increase the intensity. So we are gonna see a chart up on the upcoming slides. You can see how much more powerful it can get, but again, on the other side, we are just losing all that exposure time with the in-unit applications.
Yeah. And so some disadvantages, you do introduce the possibility of producing ozone through the UVC lights. That's anytime you get light below a wavelength of 240 nanometers. So like I said earlier, sort of the prime disinfecting range is the 265 to 270 nanometers. So, you've got a little bit of range there till you get into a situation like this. There are some titanium doped quartz tubes that can help prevent ozone production as well. Another risk is, obviously, as we talked about, human exposure. So there's a chart there. It's a little hard to read, the chart on the bottom there. That was developed by the CDC and the National Institute for Occupational Health and Safety. So it's very similar to OSHA. They look at it from more of a scientific standpoint. So that table shows you sort of the recommended exposure based on your effective irradiance. So obviously, if you're not going to be, if people will not be exposed, you can use a much higher intensity, but anything within the space, when it's going to be occupied, it has to be much lower intensity. Primarily your irritation is going to be to your eyes. There hasn't been any documented cases where we've had, where there's been, long-term damage. It's mostly short-term, like I said, just irritation. But again, it's not something good for if it's an environment you have to work in every day. The other issue that we do run across is degrading of materials. So this would happen both in your air handling system and within the space. Within the space, you're going to see discoloration of paint. And plastics tends to yellow a lot of plastics within the space. In the HVAC system, you'll see you can start to see breakdown of sealants, coatings on the coils, and within the filters, you can start to see breakdown of material, releasing fiberglass or polyester fibers into the air at that point. And so, these are some of the things to consider for UV disinfection.
Correct. And for targeting material degradation, you can either, like if you are installing this within your units, you can either provide additional filtration on your UV light so it doesn't radiate anywhere below or anywhere beyond where you'd like to have it, which increases your pressure drop, or you can tape a lot of things up with aluminum tape, which is pretty durable with the UVC light. But again, we need to make sure that we are paying attention to what we are doing especially in an existing application. If it is in rooms, we then also should look at reflection as well. If you do have a lot of screens, a lot of metal surfaces in the space, that also generates another issue down the road. So we talked about having only single pass in HV applications. In order to make that a little better, then they came up with this other technology. It still utilizes UVGI and UVC light, but then in addition to having that single pass, we are also radiating the UVC light on a titanium plate. When this happens, the titanium plate then generates or releases electrons into space, and then those electrons attack water molecules, and then at the end they create superoxide and hydroxyl radicals, which are very active ions. And these pretty much, if you are talking about VOC, these just then break the VOC, and then they generate water and CO2. If this is a virus, and then again, just like the bipolar ionization, they remove hydrogen from the virus so that it gets deactivated. It has been actually utilized in hospitals quite often, and especially airports. The major utilization for the system is mainly the VOC up to this point, but we are seeing that it can actually work for the viruses. It is the same principle. There are a bunch of different manufacturers. Some manufacturers utilize an older technology or a cheaper solution, which can then generate some byproducts that we need to be careful of. The pressure drop is actually fairly low, but again, the moment we are talking about filtering the UV light on both sides, then we are going to add pressure drop. The main drawback on the system, it is the most expensive in comparison to all the other options. Temperature and humidity. So this is another part where we can control with our HVAC systems. The smaller droplets that we talked early on, they will evaporate at any relative humidity. So it doesn't necessarily matter what the temperature or the humidity is within our space. So we can't really do anything about those small droplets. But with the larger droplets, if we do increase the humidity level between 40 to 60%, and on the other side, 40 to 60% is the actual comfort window for building occupants. The main challenge, especially over here in California, is we are not necessarily worried about humidity in our buildings, and we do not really do very much dehumidification. Because of that, we do not have dehumidification. Like dehumidification is somewhat easier than humidification. In a typical office building, you will not have humidifiers. And in order to go back and install a new humidifier, then there are a lot of things that need to be paid attention to. And the bang you get for your buck is not really that much, because you can only help with some of those larger droplets, and it is not really going to kill anything. It is just going to help. In terms of the actual temperature that kills the virus, if we can maintain 133 degrees in our buildings for about 30 minutes, it's going to kill the virus. But anything below that, it's not really going to do anything to the virus. So with the common cold, they actually have done studies about the humidity, and it was for a fact proven that if you can maintain 40 to 60%, then you're also going to reduce the transmission or reduce the infection in the buildings. As we spoke earlier, there are some of those days in California that it can be either cold and dry or hot and dry. Let's say you are about 20% RH. In order to get up to 40%, you just have to humidify the air, and in order to do that, you have to bring humidifiers in. And again, it's not very realistic in our buildings. In terms of the actual air distribution, we talked about this early on too. Majority of the buildings over here in the United States are utilizing air for conditioning spaces, and mainly force air. with the forced air, and again, maybe 80–90% of the systems are overhead systems, which means we are just providing cold supply air overhead, above head, and then we are also return air above head too. So this system just works based on mixing everything. So the moment you supply air into the space, it mixes with return air and it just goes down. So as it sounds, it is not the ideal system for contaminating anything in the airstream, because any material is just going to linger, or any particle is just going to linger for longer time in the space. With these systems, there is not really much we can do to generate isolation zones unless we can control pressure, which is being done in hospitals or lab environment. But for typical office, it is again not the way. The only way to control what we can do is pretty much play with the floor plan. And like, for example, in this case, assume the blue is the supply duct and pink color is the return air. So if we can relocate all these occupants to the perimeter, and if we just supply cold air in the perimeter, then everything is just going to come back this way and then return back through this ductwork. With that, we can actually generate some sort of isolation so that nobody is located within downstream of each other. But again, this is just going to reduce the building occupancy even further. So this could actually be feasible within the near future. But if we are talking about in 2 years, 3 years, if we are still dealing with this issue, then obviously we want to have more people in our buildings, and then maybe we will look at some other applications. And then there is underfloor distribution, there's displacement ventilation. So with the underfloor, we pretty much have a plenum right under the occupied space, and we provide cold air from that plenum. With the buoyancy, the air just directly goes up. It doesn't mix sideways, so it generates a plume effect, especially with electronics and people, because we are also generating heat. When combined with that, air just directly goes up, which provides much better isolation in terms of between cubicles, let's say in this case. So this air, the return air from the space, some will still go sideways, but majority of it is just going to go directly up. So it helps a lot. And again, with these systems too, it certainly depends on the building floor plate, what the distance is between the cubicles or the workstations. There are a lot of different considerations, and it is not necessarily one system works for all. We just need to make sure that we are paying attention to all the moving parts and then coming up with the best systems. This is actually utilized in data centers at the moment. We are just providing air from the cold aisle that is cold, and then hot aisle just takes everything back. So this is pretty much what we can generate with the underfloor system in our buildings. In terms of cold and hot aisles, we can then have clean and dirty aisles. And there are also sequence of operations. So all the equipment, HVAC equipment and the building equipment right now is smart enough to be programmed to be integrated with one another. So in our buildings at the moment, right before occupancy, around 6 a.m., maybe 5 a.m., 4 a.m., depending on the building schedule, we pretty much wash the building with outside air. It is called purge mode. So we are already doing it. It's a code requirement. As we talked about bringing more ventilation air to the space, this is one other place where we can bring in more ventilation when the building is not occupied, and it's just going to dilute the building even further. We can run ventilation or house air systems longer through the night, over the weekend. And again, this depends on what kind of an application you have, what kind of risk factors you have. Obviously, higher the risk you have, you want to run the systems much longer. Restroom exhaust is one other place. We can run restroom exhaust 24/7 at the moment. Those systems turn off when the building is unoccupied. But again, we need to pay attention. If we can also increase the system size and capacity as long as our exhaust and makeup systems allow for that. We talked about building humidity. If we do have the means, then humidifying to some extent is going to help. but again, this is not very feasible on majority of the office buildings. If you are talking about a high-rise building, it is ideal to maintain equal pressures between different floors, so we are not taking air from one floor and dumping into the other floor. Supply air reset is a code requirement. It is actually dictating us to use warmer cold air temperatures instead of 55 degrees, for example, 60 degrees, which then increases our economizer utilization in the space. So with that, we can also bring in more outside air. Demand control ventilation is pretty much the CO2 sensors. You see those in densely occupied spaces, conference rooms, for example. So what we are saying is we still utilize them for sensoring, but we are not gonna reduce ventilation if the CO2 level is below the threshold, because nowadays everybody is utilizing offices for different purposes. Some firms turn those into workstations for maybe 2 people. Some firms turn those into a location where because there are a lot of different protocols for going back to the office, you need to check your temperature or answer some questions. So some firms are utilizing offices for that purpose. So we just want to make sure that we are providing good ventilation in those spaces. Heat recovery systems, again, this is something that is not usually done in our climate, in California climate for offices. We do use those for lab projects a lot, but for offices, they do not really make financial sense. If we do have anything like that, we just need to pay attention that we are not contaminating the fresh outside air with the return air. So we just need to bypass if we can. And then we have some suggestions for the facility operations. The unit components can be contaminated, so anyone changing filters, anyone servicing coils or any equipment, they should just take precaution and use PPE. If they are working on roof, staying away from the sewer vent pipes is smart. At the moment, it is not. Again, this is one of those areas that we do not have hard data that it can be airborne from the sewer, but it has been documented during the SARS outbreak in China, so that people actually got sick from the vent pipes up on the roof. If you are not changing the existing filtration system, there is not really any benefit of changing the filters more frequently. But if you are increasing your filter efficiency with one of the systems we talked about, then the filters are going to get loaded much sooner. If that is the case, then it may make more sense to change the filters more frequently. We talked about restroom exhaust. If you can run 24/7, increase the exhaust rates if possible. And in addition to controlling airflow in restrooms, if like majority of the buildings do not have toilet seat lids, but if you have those, it also is beneficial to close those or lower those during flushing. This was another documented case in China back in the SARS outbreak that it could actually become airborne. We talked about CO2 sensors, UVGI, we talked about that. Just we need to make sure that we are controlling human exposure. If we are locating these in HVAC systems, then we need to have disconnects so that when somebody is servicing the equipment, then the UVGI system is not on. And again, same thing with the filtration or any other material that is impacted by UVGI. We need to make sure that we are taking the correct measurements for that.
So one of the things I'd like to touch on here a bit, not to make a pun there, but if you all recall when COVID-19 first started becoming part of everybody's everyday vocabulary, what was the message that was getting out to everyone was to continuously wash your hands. The reason for that is, how many things you touch throughout the day that other people touch. I mean, you look at your from the time you leave your car or leave the train in the morning, you use your hand to open the door, push the call button for the elevator, open the door to your office, everything. These are all surfaces that everybody's touching. So one of the ways is to implement more more hands-free operation in things. And so that can be everything from, automatic openers on doors, which, it's not any new technology, but something that might be reconsidered here for office environments. They can be controlled by sensors, the way we traditionally have seen them in retail stores or main entries for buildings, or get down to like biometric activation, facial recognition, that kind of stuff for secured doors. You look at the break room in your office, the coffee machine, the refrigerator, microwave, all these things that everybody's touching. You can, there's appliances out there. You can have them be smartphone activated or even voice activated. Again, just to minimize everybody's hands being everywhere. Lighting controls systems that are out there, take Enlighted or Enlighter. There's many others out there that implement smart sensor technology that and Bluetooth technology that can essentially track where people are going or where you're going throughout the space. There's ways you can adapt those systems to say open doors, or adjust controls in spaces without having the need for touching common switches and devices, that kind of stuff. Same way for AV systems. In your restrooms, the hands-free devices, lavatories, flush valves, that kind of stuff. You might start to see those become more commonly used, and even these are something that can easily be retrofitted, with battery devices that don't require electricity at all. Also, looking at elevators, you can get voice-activated controls for elevators, or even using motorized blinds. They might be a little expensive as a retrofit, but it's something that's out there that they can operate on sensors, or again by smartphone control or what have you. Next slide. Try and move through here quickly. Social distancing was has been another key strategy that's been in use. And so, unfortunately here in the Bay Area, with the cost of real estate, the drive for the last several years has been to make offices as dense and tightly packed as we can physically get them. So some of the strategies to be able to mitigate that in the future, should we, for the next pandemic, if people need to try and spread out a little more. Koray talked about the benefits of raised floor applications from an air standpoint. You can also use them to be more flexible from an electrical standpoint, using longer whips on all your floor boxes to be able to move workstations further apart should you need to. And this is something, again, that can be done very easily with maintenance staff, and doesn't require core drilling of a floor and an electrician and a general contractor, all those different parties. Also for overhead systems, utilizing more power poles, again, that can be moved around easily as opposed to a floor core. I know power poles aren't the most exciting option from an architectural standpoint, but again, looking here purely for function. Then also, if we rely more on wireless within the office space, can start eliminating some of the data cabling, again, needing less systems to move around to spread the workplace out. So then, just to kind of summarize from an electrical standpoint, we talked earlier about the benefits of using ultraviolet light within the space, either during occupied hours, or with higher intensity lamps after hours during unoccupied times. We talked about the ability to use sensor activated door openers, or hands-free plumbing fixtures in restrooms. another option again is to update the lighting control system within the space to something that is more easily integrated to all these different systems throughout the environment, and then also providing the ability to get voice activated controls for elevators, kitchen appliances, that kind of stuff. Motorized shades can help where it's practical. And then last, we talked about just creating a more flexible workspace through longer cords and the ability to move workstations around easily. So that was all I had. That was quick summary of electrical enhancements that can be done.
Hi, so we have a couple of questions, and keep typing in the chat box or the question box if you have any more questions. So the first question is that for new package units serving 2,000 square feet up to 20 and 25K cubic feet, which is the most cost-effective or practical method for disinfection and filtration? If MERV 14 filtration is used, is there any other disinfection recommended as well?
Yeah, so MERV 14, it's great if you have MERV 14s. And again, we talked about this. The very first thing to do is to analyze your building. What are the risk factors? If it is a high risk building, then you may also look at some of the other technology, especially if it is recognized that the virus can be airborne beyond that 6 feet. So if that is the case, a typical filtration system like the MERV 13, 14, I would say is gonna run around 5 cents per CFM. The bipolar ionization is gonna be around 25 cents. UVGI technology in AC units is gonna be around 25 to 30 cents. Dynamic filtration is going to be about $1 per CFM, and the PCO is going to be 1.5. So depending on what kind of risks we are talking about in the certain application, then we can just go up. With the bipolar ionization, they actually tested the system on COVID, and they did get good results, but there are challenges. Their test was in lab environment in a chamber, which is not necessarily matching our buildings, but still it's a very promising technology and fairly cheap.
So the next question is, how do you evaluate an existing mechanical system to confirm if it can handle MERV 13 filtration? Did we lose you?
What happened to him?
Oh, hi, I think I'm back.
Yep, hear you now.
All right, I don't know where I lost you, but so a quick sum on the options. First thing we do is we just check the risk assessment. We do a risk assessment in the building. If it is a high risk building, then we take some of the more expensive precautions. Typical filtration system is going to cost about 5 cents per CFM. Bipolar ionization is going to be about 25 cents per CFM. The UVGI in buildings is going to be about 30 cents. Dynamic filtration is going to be about $1. PCO is going to be about $1.5 per CFM. So you can go up if it is necessary, but MERV 14 at the moment, as of now, is good enough. But if WHO or CDC announces or recognizes that it can be airborne, depending on the building, then we may actually look at some of the other options.
Another question is that, are you concerned that so many of these solutions depend on electrical power, making the facilities at risk of utilization in event of seismic or other calamity?
Good question. So majority of these systems are going to be interlocked because they're going to get their power from the actual unit. So if you are utilizing these in units, then if the unit is not on, these spaces are not going to be on. If the unit is not on, you are not delivering ventilation or you are not exhausting either. So that's another issue. But if you are talking about in space applications, these have been utilized, and depending on the risk assessment in the building, if it is very critical, then you can actually power these through emergency power generator or batteries.
Okay, and what is the recommended number of air changes in an office space now with COVID-19, if that is a reasonable option?
Yeah, so this is again, like it certainly depends on the application. There is not really a good rate that works for everything. So at the moment, in a typical building, we are looking at 1 CFM square foot to 1.5 CFM square foot under normal circumstances. And that would equate to 6 air changes to less than 10 air changes. In regular environment, it is good enough, but again, depending on how many people you have there, what kind of system you have, then these are all different parts. With some systems, especially underfloor systems and displacement ventilation, if you increase the supply airflow into the space, you can actually make things even worse. So again, we just need to look at the specific application to make that call.
Did you say that an electronic precipitation filtration system is better than a MERV 14 system? In a small commercial space, we have the E-filter and we're questioning to replace with MERV filters instead, if better.
So the dynamic filters can go up to MERV 15, and depends on how you like to utilize the technology. So dynamic filtration, for example, is going to capture about 50-55% VOCs. When it is about the viruses, it can go up to 80-85%. So if again everything goes back to risk analysis in your building, if you are worried that you can have issues in your building, then dynamic filtrations by itself may not be good enough to provide enough coverage either. But certainly, like if you are replacing a dynamic filter with a traditional filter, certainly we need to look at the pressure drop, because the existing fan may not be able to overcome the added pressure drop from the mechanical system filtration system.
Do you think a laminar flow system feeding from underfloor and exhausting at ceiling is a likely future option for higher end office space and building?
It could be a great question. I mean, it all depends on the aerodynamics in the space. We do CFD models for some of our customers to determine what makes the most sense for some of the new ground up projects. And again, it just changes on so many different things. Floor plan is a major consideration on that. After the SARS outbreak in China, majority of the offices switched to underfloor systems. So there is certainly a benefit, but then again, we need to look at what kind of airflow we are talking about, because above some certain threshold, these systems are also going to be working the other way. So it can make things even worse.
Okay, the last question, with indirect UV above 7 feet, how does that deactivate pathogens at the human level where droplets are falling?
So with the thermal stratification, hot air rises up and it just carries all the pathogens or contaminants to above wherever we are returning air back. So depending on what kind of height we have, what kind of load we have, sometimes just a passive system is going to be good enough, but sometimes it can be actually beneficial to install those ceiling fans just to generate some air movement from below into the plenum space.
Great. Thank you so much for your time and everyone for attending this webinar. And all the recording and the slide decks will be made available to attendees. And yeah, thank you so much for attending. And we look forward to see you next time. Bye.
Thank you.